Okay, so let's keep trucking. I will integrate a couple of things into today's lecture based on some of the questions that came up from folks during the readings for today. So just as a quick review here, and like I said last time, we're going to spend hopefully the rest of this week and maybe one day in the next week kind of doing this review stuff, and then we'll be pretty heavy into coding during class. So some of this stuff is kind of intro stuff, but also very important. You'll see why I reference back to it pretty often. All right, so last time we talked about the idea of what is computer programming, what's the job of a programming language, kind of got some vocabulary words out of the way here, like protocol just equals language, and we're all speaking the English protocol in here. We talked about why programming is hard. It's that human beings are really good at solving problems, and it's difficult for us to articulate how we solve them, break things down into those little tiny steps. If you noticed, I posted a news article on Slack. I think it was on Friday night or Saturday morning, something like that. That was a pretty interesting article that kind of mimicked several of our slides here. We talked about how do human beings solve problems. So I kind of break this down and say, okay, we use our memory, we ask questions, and we use repetition. That's how we solve problems in real life. Now, the job of a programming language is to allow us to communicate with that computer. While we speak English, the computer speaks zeros and ones. Okay, so we can decide that we want to be, fair and meet them halfway. So we come up with some sort of hybrid language that's somewhere between English and zeros and ones. But human beings are greedy, and we decided that we don't want to go halfway. We only want to go as far away from English as we possibly have to in order to come up with some sort of tool that allows us to talk to the computer. All right, so we talked about what language the computer speaks, zeros and ones. We want to have a programming language that's as close to these natural languages as possible, but we can still somehow have a tool that converts it into the language that computers speak. Now here's that mapping slide that talked about how do human beings solve problems. We use our memory, asking questions, and repetition. I made a statement last class that said something along the lines of 100% of programming languages will have facilities for these three things. Okay? If it doesn't have facilities for these three things, it's not a programming language. That doesn't mean it sucks. It doesn't mean it's useless. It's just not a programming language. So we used an example last time like HTML. Seems like this guy is always the one on the fritz. Like HTML, not a programming language, and we'll talk about that more over the next several days, let's say. Okay, so now we're going to have a series of slides that all kind of say the same thing, but view programming languages from some different angles. All right, so we have three kinds of programming languages. We have machine language, we have low-level language, and we have high-level language. All right, now all of these have to do with the CPU. All right, so before I go into more details here, let's create another slide that talks about the CPU. What is the CPU? Okay, so central processing unit, that's what it stands for. What is it? What does it do? What's the job of the CPU in your computer? Can your computer work without a CPU?
No.
Good.
It takes the input and translates it into binary, so it can process.
Okay. That translation happens before the CPU. The CPU itself is always going to eat zeros and ones. It's always going to be processing zeros and ones. Go ahead.
Carries out the instructions of a computer program by performing the basic arithmetic, logic, controlling, and input/output operations specified by the instructor.
So you memorized all that, really?
No.
So translate that for me. What does that mean?
It does the processing. I don't know.
All right, so if you remember from last time, I mentioned that I kind of like to think about one thing we have in technology, one thing we have in really higher education, people with PhDs like to come up with really fancy names for easy things because it makes us sound smarter, right? Okay, but the idea is, and it's even worse in technology. So whenever you go and buy a new machine or buy some new thing that just came out, they usually have some really fancy name for like the technology that's in it that actually means the same thing as the name from last year, but it sounds cooler, so you think it's worth the extra $50, right? Does that make sense? We see it with the big screen TVs all the time where they have all sorts of different, like 90 different ways of showing the black color, right? They just keep coming with the HDR and HDR plus and, time travel and all that other stuff. Okay, so when we talk about the CPU, we can come up with a really complex technological description for it, but I like to think of the CPU like this. It's a collection of magic tricks that, when performed in a certain order, a real problem might be solved. All right, now one thing we want to keep in mind, and you've seen this already with me trying to create this mapping between how do human beings solve problems and how do computers solve problems, or how do the tools between us and the computer help us solve problems without us changing our ways too much. How many of you, so we're going to do a little exercise. Everybody put their hand up. How many of you can do this? Man, every one of you can do that. Okay, what about just isolating just the thumb? No. How many of you are impressed that I can do that? It's not impressive, right? It's not an impressive thing that I can do these little tiny things. Now, what can you use that one movement for? Is this one little movement? It's unimpressive in and of itself. In fact, you might just laugh at somebody if they're sitting there in the cafeteria just going like that. Okay, right? But if you think about it for a second, is this one little movement, is that part of a lot of things that we do? If you go to pick up a coffee mug, do you have to do that one tiny little move as part of a collection of moves that ultimately get that coffee cup picked up, right? That's what the CPU is. We're an example of the CPU. We can do all these tiny little magic tricks. I can do one finger. I have this joint here. I can twist like that. I can operate off this other joint. All these little things that you're going to think the person's spazzing out if they're just sitting there messing around with that in the cafeteria, but those are important little building blocks to solve real life problems that you deal with all the time. Now, when you go to pick up that coffee mug, you're not thinking about those 90 little magic tricks you're employing to pick up the coffee mug. Like, okay, now it's time to bend the thumb, right? You don't think about that, but you're doing it, right? That's what the CPU is. The CPU has built into it this collection of magic tricks, this collection of things kind of like that, or kind of like that, that are, the people at Intel or the people at AMD have kind of decided, here's the giant list of little tiny moves that, when put together, allow you to solve the generalistic collection of problems that you might want to solve with a computer. Make sense? And then when the next processor comes out next year they might say, okay, well, we left a magic trick out. Oh, or by the way, we actually found a better way for you to pick up that coffee mug. No longer do we let the thumb work like this. We just kind of hold it in this position. Okay, because it's faster. If it just sticks there, it's faster. Now you can just kind of use it for these different things. And even though it seems less flexible, it actually solves 90% of the problems more quickly. Something like that. So they're always optimizing these processors in ways like that. All right? So what ends up happening is each year, when you come out with most of you are probably running computers with Intel processors in them, right? A couple of you might have an AMD processor or something like that, but they're all Intel compatible. Well, when next year's model comes out and you're buying the 9th or the 10th generation Intel Core i7 processor, and it'll, the advertising will say, oh, it's up to 60% faster, right? The reality is it's the exact same speed for probably 95% of all tasks. Where is it 60% faster? It's 60% faster in those one or two areas where they enhanced the processor a little bit. They added a magic trick. They reworked one of the magic tricks. They did something to that processor in order to solve one specific task more efficiently than it could have the year before. So now they can legally say it's up to 60% faster. right? And it might be something you never take advantage of on your particular computer. Now, why are they able to do that? Because if you build computers, how many of you have built a computer before? A couple of you? Okay, well, one thing you'll notice, now, every now and then the form factor does change for the processors, but generally speaking, the Core i7 processor today is the same physical size as the Core i7 processor from 6 years ago. Okay, same size processor. Sometimes you'll have pins change or something, but the actual physical size of the chip remains the same. Well, each year you see this new number that comes out, like, it'll be 14 nanometer, then it'll be 12 nanometer, then it'll be 9 nanometer. This is how good our technology is getting at getting the little transistors on the CPU closer and closer and closer and closer together without them conflicting with each other and without the processor catching fire the second you turn it on. It's like that balance between function and death. Right? So as our technology improves and we're able to squeeze more and more and more stuff onto that same real estate, we can add some magic tricks. Now, we don't want to change the functionality of old magic tricks. We can maybe optimize the way they work, but the inputs and the outputs need to be the same because we want the software you bought last year to still run on this year's Core i7. Does that make sense? So when you go out and you buy an operating system or a game or something like that, it tells you what the minimum system requirements are. And when it gives it to you for a processor, it'll say minimum system requirements are as a, Core i5, 6th generation or something like that. What it's saying is that we rely on the magic tricks that were available from that period of time forward. There was at least one magic trick that was not available in the Core i5 the year before, that this game has been compiled, we'll talk about that shortly, to assume is there. That make sense? All right, so the CPU ultimately is the dude who follows that list of magic tricks to solve some problem. Just like we might follow a list of little magic tricks with articulating our fingers and stuff like that to ultimately pick up a coffee mug. All right, so kind of simplify what a processor does. Now, come back to this slide, 3 kinds of programming languages. Machine language, we've already talked about this. This is zeros and ones, all right? And we're all pretty convinced that we're not going to sit there as humans and use the 2-button keyboard just tapping out instructions to the computer. Okay, that's not for us. Okay, remember, we're greedy, so we want it to be a lot closer to English. Okay, definitely not zeros and ones. Low-level language. This has a 1-to-1 relationship with the CPU. And I'll talk about that here in a second. Whereas a high-level language has a 1-to-many relationship with the CPU. All right. If we want to put this in human terms, this is a manual screwdriver. This is one of those power drills. Okay, and humans like power tools, right? Except you got to make sure you use it for like the right task. Like, don't try to screw in one of those little like the light switch plastic covers with a power drill on high, because you'll crack right through and go into the wall, and then through the wall. It's a thing. All right, so low-level languages. We want to kind of give a name to these. An example of this is a language called assembly language. All right, when I say a 1-to-1 relationship with the CPU, what I'm saying is if you're a programmer who is writing code in a low-level language like assembly language, you have to tell the CPU each individual magic trick that they need to perform in the right order in order to accomplish a task. The real-life example of this would be if I have a coffee mug sitting here, and we'll put my... I left these here for somebody last week and they didn't take them, so we'll use them again. So if I have these things sitting here and I want to describe the solution to the problem of picking those up and, I don't know, throwing them at our sitting down robot over there. To do this in low-level language, I have to tell it each individual thing. So let's just assume my hand's already here. I have to say, okay, well, we're going to bend the pinky, then bend the ring finger, middle finger, thumb, articulating all these little things, all these little instructions. Okay, now we're gonna put power into this muscle here or this joint or whatever I'm doing internally here to ultimately accomplish this. All of those little tiny baby steps we have to articulate each and every one if we're writing something in a low-level language. One-to-one relationship with the CPU. Now, where it's friendlier for humans is we don't have to describe those magic tricks in zeros and ones. Okay? Because if we think about this, the CPU has this collection of magic tricks. Well, maybe magic trick 0001 is this guy. Magic trick 00010 is this guy. So on and so forth. So we don't have to tap out those magic tricks in that format. But we can say, bend your thumb, bend your index finger, things like that. We can give it that instruction in kind of an English-like way, but it's still only this little tiny move. That makes sense? So we're going to call low-level languages palatable for humans, if forced. Because it is English-like, we just have to really drop things down to those little tiny individual steps. Now, a high-level language, this is our bread and butter. So these are languages like you've heard of. So Python, Java, C++, C, C#, blah, blah, blah. We can just keep listing every language you've heard of probably, and they're all high-level languages. These have a one-to-many relationship with the CPU. We write one line of code in the CPU, and it translates into a whole bunch of lines of code for the, we write one line of code in a high-level language. It translates into a whole bunch of magic tricks on the CPU. Okay? Now let me show you that example. Well, first, we'll just go out here. When we first write a program, we always write the hello world program in any language we're trying to learn. So in Python, hello world is print hello world. Done. That's it. Hello world in Python is just like that. Now, let's go and look at hello world in assembly language and really understand how things are working under the hood. All right, so we can see that. So I'm going to walk through this code here. Now, I'm first of all going to tell you, this code here actually has a bunch of magic tricks. It has like some power tools built into it. So if you were really to expand this out, this is hundreds and hundreds and hundreds of lines of code. When we write our low-level language like this, if we were writing it to talk directly to the CPU, that one-to-one relationship, we'd have hundreds of lines of code to accomplish this. But instead, this code here is written to talk to the operating system, which then talks to the CPU. Okay, so this assumes the operating system is Linux, but it could be Windows, it could be the Mac OS. The example still follows through. Okay, so I'm going to walk through this line by line so we understand how computers actually work with our operating systems. All right, so don't worry about this top stuff. That's just format. This is where the program starts right here. So actually, the parts that we care about is that stuff right there, and then these couple of things down here. All right, so let's talk about these couple of things down here first. We talked about that the three ways human beings solve problems is through memory, asking questions, and repetition. So if we want to remember things, we're going to create a variable here called message. This guy is going to be equal to we'll just call it a string here. It's a double byte or data byte called hello world. Okay, so we're going to say that's us storing the message we ultimately want to spit out. This guy right here, another variable called len. This is the length of that message. All right, so all I'm doing here is I'm remembering two pieces of information. What's the message I want to spit out, and how long is it? All right, we won't go any deeper into it than that. There's some more going on there, but let's just say that's it. All right, so now up here. This is us talking to our CPU in a one-to-one manner. Every single line here is telling us to do a single magic trick on the CPU. So what are we doing first? Now the CPU has built into it these little things called registers. They're kind of variables made out of hardware, really expensive memory. Don't worry too much about that. We talk about all that stuff in 325, the computer organization class. But for here, they're just little buckets of memory that we can remember things in. So what are we telling the CPU to do first? We're saying we want you to move something. What do we want you to move? We want you to move the value stored in that variable into this bucket. Next thing, what are we going to do? We're going to tell the CPU to move the value stored in this variable into this bucket. Then we're going to say we want to move just randomly the number 1 into this bucket. We'll talk about what that 1 means here in a second. Next, we're going to move randomly the value 4 into this bucket. Then we're going to interrupt the CPU, and we're going to tell the operating system to take over. Okay, so we're actually kind of passing the buck to a superhero who's going to go in and do a whole bunch of heavy lifting for us. And when this operating system goes in, when it takes over, it's going to first go and it's going to say, I'm going to go to EAX, that memory location. I'm going to look in there. I find a 4. What does a 4 mean? A 4 tells it we are going to perform super magic trick system right, which means the operating system has already written this giant program that knows how to display stuff on the screen. Okay, so that's the program we're going to run related to the operating systems. That's a whole nother assembly language program that's hundreds of lines of code that knows how to talk directly to your graphics card and all that stuff to ultimately get stuff out on the screen. So this one line here is a super magic trick that we didn't have to write the code for. So we're still being lazy, okay, because we're leveraging these fancy modern day operating systems. So the operating system is going to go and look in this bucket and say, oh, I found a 4. What does 4 mean? 4 means you want me to perform the sys-write super magic trick. And the sys-write super magic trick requires 3 inputs. I need you to tell me, where am I writing this to? What am I writing? And how long is what I'm writing? So I need 3 inputs to this function. Just so happens it's going to look for the where in EBX. It's going to find a 1. What does 1 represent? It's the file descriptor associated with standard output, which is the monitor in modern computers. So we have standard output, standard input. Standard input's the keyboard, standard output's the monitor. You know, you could have output that goes to a USB stick, stuff like that, but standard out is the monitor. All right, so what are we going to do? We're doing a sys-write. Where are we writing it? To the monitor. What are we writing? It's going to go and look in ECX. We're writing this message called hello world, containing hello world. And how long is it? Because this guy actually just points to the beginning of some place in memory. And we need to know how long it is so that we don't keep writing after that. So we're going to read the first byte, which is the H, then the E, then the L, then the L, then the O, then the space, then the W, so on and so forth. We want to make sure we stop once we hit length. And we don't just keep writing the random stuff that's in memory past that. Okay? So these lines right here ultimately will spit hello world to the screen using our operating system, in this case Linux, as our power tool to do all that magic of getting stuff from memory actually out to the screen. So as an assembly language programmer, all we had to do was stage some information in 4 different little buckets. We just put stuff in these 4 buckets, told the operating system to take over, and it did the rest. That's how modern day assembly works. Go ahead.
Why is it that I usually hear about like different operating systems instead of Linux? Like, why is it less used than Mac OS? Or
What do you mean less used?
like, at least I just don't hear of it. Maybe I just like, but no, I've never heard anybody saying like, oh, my computer runs on this or like on that.
Oh, like why is Linux less popular?
Yeah.
It's probably because today you can make the argument it's not as less user-friendly, but our mainstream operating systems, like the operating system you want to put in front of grandpa, is probably like a Windows or a Mac system because it's built for, let's call it, normal people, where Linux is kind of built more for programmers or for tech people, where there's less fluff there, so you almost feel like you're really using your computer. You can make the argument you could be a lot more powerful with Linux. In fact, I'd call Mac OS pretty similar to Linux, just because you can basically open a terminal here. This is the reason why Mac OS is effectively Linux, is you can give it command line stuff like this, where the command prompt on Windows, which is just a DOS prompt, is far less powerful than that. But you know, we're going to call these guys relative equivalents: Linux, Mac OS, Windows, because they all have the idea of these system calls. Windows is going to have its equivalent of syswrite. These are kind of the go-to things. All operating systems know how to tell the graphics card to put something on the screen. Doesn't matter which it is. But certainly Linux is less popular, probably just because of its history. And a lot of that is Microsoft's big advertising budget and things like that. You can even make the argument, I run a Mac here, but I have a Windows machine in my backpack still. So I'm not pro any of them, as I'm always about the right tool for the job. The people who are kind of Mac fanboys who say that, the Mac is so much more user-friendly, I'd almost make the argument that Windows is more user-friendly. Especially if you're throwing this down in front of Grandpa, where do you start? You click the start button. That's where Grandpa starts. Set the start button. Where the Mac, once you learn the cadence of that operating system, maybe you can say it's pretty user-friendly and easy to work with and stuff like that. But there's a learning curve with any of them. But the learning curve for Linux is definitely bigger.
Oh, yeah.
Yeah. So, but I'd encourage all of you to dabble with Linux. I think Mac is pretty similar as long as you convince yourself to go out to the terminal. You're going to see a lot. Throughout your years in computer science, you're going to have me for any class that deals with programming or the technical stuff in computer science. So you're going to have me many times. So you'll see lots of examples of that stuff. But I encourage you to dabble with Linux at some point, or if you already have a Mac, dabble with terminal commands and things like that, because I think it's fun and it's a skill that will set you apart. Because young people today, they're not seeing that stuff that was very commonplace 15 or 20 years ago. Because everything has a GUI on it now, right? Double click on this, hit start, hit the little play button, things like that. So a lot of magic is happening for you behind the scenes. And one of the things I like to do is I like to show you how things are actually working under the hood. Sometimes we'll actually go and do this as just an exercise of, really appreciating the power tools we have today, but usually we're using modern day tools that will have that play button, right? If I'm running this program as an assembly code, so you're going to put this in a text document, but then you actually have to go and get an assembler, be out at the command line, run the assembler against this code. It's going to link it to the operating system. It's going to do all this stuff, and you're like doing all this at this little command line with no graphical user interface. That's not normal for the modern computer user who has been using computers for the last 15 years or 17 years, something like that, because we haven't had those kind of details to deal with. We've always had icons to double click on. And we can say life is better now. That's fair. But sometimes, let's call it 5% of the time, you need one of those skills that you would have had doing it the old way. And now when you don't have it, things become a lot more difficult in your head. Okay, so modern assembly language code, when we're writing low-level programs, we're still ultimately talking to the operating system, where a long time ago we would have been talking directly to the CPU. So this is still a power tool. All right? So all we're doing here is we're staging up some information in 4 different buckets. Then we're telling the operating system to take over. Then what are we doing? Now notice the very first thing I said after we told the operating system to take over here is the operating system went and looked inside of EAX. And EAX tells you, what is it that you want me to do? Now up here, because it had a 4 in it, it said, I want you to do a syswrite. And syswrite required 3 inputs. So I went and grabbed its 3 inputs from these 3 other buckets. Okay? So it was very important that we put those inputs in those specific buckets. It was requiring that. Now down here, when we come back to the program, notice we're overwriting our 4 that was in EAX with a 1. And then we're interrupting the CPU again. So these 2 lines and these 2 lines are effectively doing the same thing. We're putting the instruction inside, the instruction number inside of EAX that we want the operating system to do. And then we're telling the operating system to go. Up here we had a 4, which required 3 inputs. Down here we have a 1, which is related to sysexit, which just says, tell the program to close. Exit the program. That doesn't require any inputs. So that's why we didn't put any other stuff in any other buckets. We threw a 1 into EAX, told the operating system to take over. Operating system went and looked at EAX and said, we're done. Program's over. Closed the process, freed up the memory associated with it, all that stuff. So even in this example here, which looks kind of cryptic, we're doing a lot of heavy lifting with that operating system. The operating system does a lot of stuff for us. All right, that makes some sense? Now, what I'm telling you as a modern day programmer, you will spend less than 1% of your time doing stuff like this. It's not that it's not awesome and fun. Okay? In fact, you'll have a couple of classes with me where you'll only be writing this stuff. And you'll find it awesome and fun and terrifying and ridiculous and all that stuff because it's fun. But it'll make you appreciate our high-level languages. That make sense? Now, a follow-up question might be is, do we ever need to use this today? Do we really ever need to use this today? So let's put a pin in that for a second, and we'll answer that in, call it 3 or 4 minutes. So we go back to the high-level language, one-to-one relationship, or one-to-many relationship with the CPU. So we are going to write our hello world program in Python like that. And then when we run that program, it's going to translate it into something that looks like this, which is then going to get translated into something that's a bunch of zeros and ones that ultimately the CPU understands. So we have a couple of tools that are going to sit between us and the CPU that allows us to write code like this and then run it through 1 or 2 tools that ultimately will put it to the CPU in a bunch of zeros and ones so that we didn't have to do that ourselves. That make sense? All right, so remember I said we're going to have several slides that kind of start off this similar kind of way? There are 2 kinds of programming languages. This is from a different angle. We have interpreted languages, and we have compiled languages. All right? Now, interpreted languages are translated from high level to low level at runtime. Compiled languages are translated from high level to low level prior to runtime. Okay, so if we want to think about a real life example of this, let's say that the president's giving a speech and it's being, he's giving it in English and it's being broadcast all over the world in a bunch of different languages. The interpreted version of this would be while the president's up there speaking in English, each country has an interpreter that's listening to the real-time commands, the real-time English, and then spitting out the German or the Japanese or the Chinese, that kind of stuff. So there's going to be a little delay, right, as they're translating from English into their native language while it's currently running. So we're going to say this guy is relatively slow. Now, with an emphasis on the relatively, because computers are really, 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 really fast. So just because it's relatively slow to a human being, 99% of those programs might feel like they run instantly anyways. So that's okay. We're not going to say interpreted languages are bad. In fact, we're going to give an argument for why they might be kind of good. In fact, Python is an interpreted language. Now, the flip side here is a compiled language is relatively fast. We spend some extra time beforehand so that same speech, instead of waiting until the president gets up and starts spouting stuff off in English and doing the translation then, all these countries, they got a copy of the English version of the speech, and then they had a couple of hours, let's say, to go through and translate it into their native language. So that during the speech, they were able to deliver the actual words in German or Chinese or whatever in real time without having to do that interpretation while it was running. Does that make sense? So we did some more work up front, but while the program was running, it was faster. Make sense? So we're going to say that's relatively fast. Again, doesn't necessarily matter. We're going to say most of the time, probably not. All right? So now, just because these languages are relatively slow, these guys require something called an interpreter. All right, so the real life version of that is if you have a German news station, they're going to need somebody who speaks both English and German. They need that dude okay, who can go there and listen to the English and turn it into German at the same time, or in relative real time. Okay, so these guys require an interpreter. These guys down here, and this is where it differentiates from real life a little bit, because we probably figure that the same dude from up here could probably take a handwritten speech and turn it into German as well, right? Computers, it's a different tool. So these guys require something called a compiler. Okay, different tool. So we have a tool called an interpreter, we have a tool called a compiler. Having said that, there are two kinds of programming languages. Interpreted and compiled. Interpreted and compiled languages. So now what's an interpreted language? So we're going to say an interpreter here and a compiler here. An interpreter is a computer program usually written in a high-level language that will translate in real time high-level code to the equivalent low-level code. Compiler is a computer program usually written in a low-level language that will translate prior to runtime high-level code to the equivalent low-level code. So both of these guys do relatively the same thing. The thing that changes is when do they do the work. Now, within the last several minutes, we've looked at the difference between low-level and high-level code, right? So we saw the high-level version of Hello World, which was 1 line long in Python. We saw the low-level version of Hello World, but we saw the power tool version of that, which was like, 20 lines of code. But reality, under the hood, it was hundreds of lines of code, if we factor in what those system calls from the operating system actually had to do. So low-level code, a lot harder to write, like a lot more time-consuming to write, certainly. Probably harder to write as well. Because in that case, it's like picking up the coffee mug. We have to give each little instruction. What do we do next? What do we do next to articulate to pick up the mug? Where in a high-level language, we just say, pick up the mug. Okay, and behind the scenes, there was the collection of 50 magic tricks. When we compiled it down to those steps, we already in our head know how to pick up that mug. Okay? So we, as programmers, we probably prefer working in high-level languages. Sounds right? We'd rather write a single line that says hello world than a whole bunch of code to say hello world. All right, it's interesting to understand what's happening under the hood, but we'd rather use those high-level languages. So we think about how every week, and you'll probably notice this more now that you're getting into computer programming, there's new programming languages that get released. Okay? Some of them become popular. Other ones are just kind of, like somebody in their dorm room decided, hey, I'm going to write a language called XYZ, and it's so much better than these other languages that have existed for a long, long, long time, and maybe it's good at solving a very specific kind of problem. Because it has some power tools built into it specifically for solving those problems. And it becomes this language that is popular among like him and his 8 friends, which is okay. There's nothing wrong with that. That's a domain-specific language that might be great for the exact kind of things that they're writing. Maybe they're writing a certain kind of video game or something like that that really relies on a very specific type of logic that writing those tools up front and then using them over and over and over again is helpful. Okay, but generally speaking, when we think about our popular languages today, these are general purpose programming languages that general purpose programmers can sit there and say, okay, well, I'm going to use this language to solve all sorts of problems on the computer. And we kind of have a collection of languages that have become popular for that. And every year, 1 or 2 new languages kind of come out and they gain a little traction, and they might solve some problem that wasn't, was a little bit cryptic from the previous tools that were out there, like maybe memory leaks, or they take a little bit of extra work away from the programmer. And you'll see some examples of that as we kind of work through the history of our languages here. But the punchline is that we can have new programming languages come out pretty often to solve very specialized types of problems if those languages can have interpreters written in a high-level language. Any one of you in here, after possibly this semester, but certainly after next semester with programming, would be able to sit down and write some sort of kind of hacked together interpreted language that maybe makes some solution to a problem a little bit easier to write, because you're able to write that language in a high-level language. You're just doing direct translation. Okay? Now a compiler, this guy's a lot harder to write. First of all, you need to have a very formal definition for your programming language, the syntax of your programming language, and then you have to write hundreds of thousands of lines of assembly code that ultimately will translate high-level code into zeros and ones. It's a much, much, much harder tool to write, so you'll find far fewer compiled languages come out each year. Most of our languages, and a lot of times you hear interpreted languages referred to as scripting languages. All right, so if we want to often called scripting languages. Okay? And these guys have become very, very popular because we're able to rely on how fast our computers actually are. So even though, if we look under the hood, they're actually relatively slow, they're fast enough for most of the stuff we're going to use them for. I wouldn't say one's better or worse than the other. Realistically, compiled languages are what we're going to use to write all of our video games. Things that just need to be super, 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 super fast. And with that in mind, when would we still use assembly? So if we're writing a video game, and most of our modern programming languages, and we're going to see this through plenty of examples this semester, they require you to write completely unambiguous code. Your instructions that you write have to be very unambiguous, such that the computer knows exactly what to do under every little circumstance. Okay? Now, as a human being, you might be solving a problem where you happen to know, based on the nature of the problem you're solving, that some condition would never occur. Make sense? Take a real life example. If you are making a milkshake in your kitchen, you're pretty sure that you don't need to be worried about getting hit by a car. Just using a kind of an extreme example, right? Now, it could happen. Somebody could really, really swerve. Okay. But you're pretty sure that getting hit by a car in your own kitchen is one of the least things you need to worry about. But now in a computer program, you might need to take all conditions into consideration under a certain example. So you might have if I haven't been hit by a car, do this stuff. Else, cry and bleed, or whatever, whatever the else is. Okay? You would actually have to write that into your code. And that would get translated into the low-level code for your CPU. That technically, because we had to ask one extra question there. I'm getting ready to hit the button on the blender, and instead of just immediately hitting the button, I have to look around to make sure I'm not about to get hit by a car. In real life, we wouldn't do that. A computer might make us do that, just in case. Make sense? All right, so we might decide in a video game, how many of you are gamers in here? We usually get quite a few of those in computer science. How many of you are PC gamers? All right. How many of you spent more money on your graphics card than you did on your car? Who doesn't want to admit it? All right, so why do you? So how many of you have what you consider to be a fairly powerful graphics card in your computer for your PC gamers? Okay, so you have these cards that cost $500, $600, $700, $800, $1,000. I mean, there's cards today that are $2,200 for the newest, latest, greatest thing. Now, when you're playing a video game, the human eye can roughly see, let's just call it 60 frames per second. That's a little bit of a lie, but let's just call it that. Okay? Now, somebody who spent $100 on their graphics card might be able to play a certain game at 60 frames per second, just like somebody who spent $1,000 on a graphics card was able to play that game at 60 frames per second. Does that mean the person who spent the $1,000 on the graphics card wasted their money? Why did you spend the $1,000 on the graphics card other than bragging rights? Under what circumstance does that card actually help you in that particular game? A lot of our modern games are online games, right? All right, so you might have 1,000 players playing at the same time. And maybe 90% of the time when you're playing the game, you're kind of out and about, kind of by yourself, or maybe 2 or 3 other players are on the screen or something, and you're able to maintain 60 frames a second with your $100 or your $100 graphics card. And the guy with the $1,000 graphics card, he's able to maintain, well, technically he's probably getting 800 frames per second, but his monitor can only spit it out at 60 or 120, okay, whatever it is. But they're basically equal views. Then all of a sudden you go into the main city. Okay, and there's 1,000 people all with explosions and all this other stuff happening on the screen all at once. Okay, and all of a sudden the person with the $1,000 graphics card goes from 800 frames per second down to 170 frames per second. Still doing pretty well. Way faster than this monitor can show. Okay, where the person with the $100 graphics card is now looking at a slideshow. Getting 3 frames per second or something like that. There's this major delay. He comes back on the screen. He's actually died already. The game has ended, and he missed his chance to even enter the next game. That's how backed up his system was. Okay? So you get the point of something like that. We have these power tools for solving problems like that. Now, the people who write those video games. So let's take that example of. You walk into that city that has a zillion things happening at once. I realize we're out of time, so let me just sum this up in the last 30 seconds. You go into that city, but you've written the software for it. Now, we want that person who spent the $100 on their graphics card to not have a horrific experience or have the best chance of having a reasonable experience. So as the programmer, you're going to say, okay, when we walk into the city, okay, we don't have to worry about whether or not some situation that cannot happen or just would not happen. We don't have to ask the question about whether that should happen. That comes back to our making a milkshake. Do we need to worry about getting hit by a car? The high-level language might actually have us put that logic in there because it might require it. And then it's going to turn it into low-level code that also has that question being asked, checking, is there a car before I push the blender button? You can then go into the low-level code as a programmer and take that question out and say, I know this condition would never happen. We're just going to hit the button on the blender and not look for the cars because that'll make the problem a little bit faster. That make some sense? All right. So that's kind of the example where these things might pop up. All right. Questions, comments, concerns, bribes. All right, I will put the next Bible homework up and the next reading assignment. I want to make sure that I want you to do the reading assignment, so I'll look at it here in the next half hour. We'll hopefully get through these slides this week and be able to jump into some programming. So right now I'm kind of having you limp ahead a little bit in Python just to get the intro stuff so that I can come back through and fill in the blanks from what we're talking about here. Sound good? Yeah. I will see everybody on Wednesday.